Algebra 1 Lesson 83, we are factoring one more time, and we are looking at some patterns and special products in order to make factoring a little easier. So first of all, let's think about the opposite of factoring, and that's multiplying out, actually expanding. And we've seen this pattern before. This is a square binomial, which means that when we actually multiply out, remember that we get the square of the first term, the square of the second term, and then we multiply the two terms together, so x times 1 and then times 2, so we get plus 2x. All right, and you can prove this by foiling, but like with the next one, we will get the square of the first, the square of the last, and then multiply them together, get 2x, multiply it by 2, and get 4x. Which means, or I'll show you these other two as well. Okay, similar idea here, square of the first, square of the second. Okay, remember -1 times -1 is a positive 1. And then we get -1x times 2, so minus 2x. And we get x squared minus 4x plus 4. Which means when you see this pattern in a trinomial, you can then say, well, I can use that pattern to work backwards to find the factored form. So remember that if you have a square binomial a plus b, it will give you a squared plus 2ab plus b squared. Which means if we're working backwards, I could say, if I have this pattern, that means the first part of my term is going to be the square root of my quadratic term of this a squared. The second part is going to be the square root of my last term, my constant. And I just need to make sure that this middle term is the combination of those two square roots times 2. So let's try it. And same idea with a negative in there. So if I have x squared plus 6x plus 9, well, I definitely have a square on the first and a square on the second, which means the question is 6x a combination of those two? Well, that means it needs to be the square root of x squared, which is x, and the square root of 9, which is 3, times 2. And we do get 6x. So I can say the factorization of this is x plus 3 squared. And if you were to work that out, it does give you x squared plus 6x plus 9. So once again, x squared is a perfect square, so is 49. So we just need to check if this internal term is 2 times the square root of the first, so x, times the square root of second, 7. And it does give me 14x, so that works, which means I can just put x plus 7 squared. All right, so we're looking for that perfect square to start and finish our trinomial and the combination in between. So let's try a few more. X squared minus 4x plus 4. So we have a perfect square, perfect square. So let's see, is this the combination of 2 times the square root of our first term, x, times the square root of our second, 2? And we say, yeah, except that this 2 must be negative in order to give us a negative 4x and give us that positive 4 at the end. So we must have x minus 2 squared. All right, next one over here. We have a perfect square and a perfect square, but when we look at that perfect square at the end, I have a negative 64, and I'm saying to myself, is there anything that would actually give me that negative 64 if I'm looking at a perfect square? And we say no, because I have to have something times itself. And if I have 2 negatives, I'll get a positive. 2 positives, I get a positive. So I'm not going to get that negative 64. This still may be able to be factored, and you can use some of our other methods, but with our perfect square trinomials, it's not going to work with that pattern, so we'll just move on. All right, for 36x squared minus 48x plus 16, we have a perfect square and a perfect square, which means that the square root of this one is 6x. Square root of this one is 4. So let's see, is this a combination of 2 times 6x times, well, it must be a negative 4. And we say, well, 12 times negative 4 does give me a negative 48, so this must be 6x minus 4 squared. All right, one more time. Perfect square and perfect square here. So the square root is 4x and 3. So this needs to be a combination of 2 and 4x and a negative 3. which when we look at it, 2 times 4 is 8 times negative 3 does give me a negative 24. So I get 4x minus 3 squared. All right, we're just following patterns in order to factor these so that we don't have to go through the whole process that we've been practicing. We can find other ways. So here's a good word problem for this. A cell phone tower's signal covers a circular area with a radius r in miles. The strength of the signal is increased and now covers an area of pi r squared plus 10 pi r plus 25 pi square miles. By how much did the radius of the coverage increase? Well, we basically need to compare the original, which should be just pi r squared, to this new square miles. But I want to factor it. And the first thing I want to factor out is the pi, so that I just have r squared plus 10r plus 25. And I see that this is a perfect square binomial, which I can then say, all right, r squared is perfect square, 25 is perfect square, and 10 is a combination of 2, r, and 5. So we can say this is r plus 5 squared, which means if we compare our first area and our new area, we see they follow the same pattern, pi r squared, pi r squared, which means that my r has been increased by 5 miles in order to get my new coverage. So my increase is 5 miles. Okay, we can see that by factoring and getting it back to its original, more typical area formula for a circle. Now we have a second way to find some patterns in our trinomials, and that's with a difference of two squares. So we have a squared minus b squared. That gives us our a plus b times a minus b. We've seen this pattern before. A plus b times a minus b. We have the same first term, the same last term, but the only thing that's different between them is a plus and a minus. And it gives us this perfect square to begin with, perfect square to end, and just the difference in between. Which means I can look at 4x squared minus 25 and say it's a perfect square and perfect square with a difference in between. So that I can factor it as the square root of 4x squared, which is 2x. Okay, that's going to begin each of my terms. And the square root of 25, which is 5, that ends each of my terms. And I put a plus and a minus. Okay? So let's try it on a couple more. 9m to the 4th minus 16n to the 6th. These are both perfect squares. So I can say, all right, the square root of 9m to the 4th is 3m squared. Okay, that starts off each of my terms. And the square root of 16n to the 6th is 4n to the 3rd. 4n to the 3rd. So then I just put a plus and a minus in between. All right, the next one, unfortunately, doesn't look right now to look like a difference of squares, but maybe if I take out a 2 from each of them. So I have x to the 6th minus 144. And I see that, yes, this is a perfect square that I can split up into square root of the first and square root of the second with a plus and a minus in between. So sometimes we need to factor out that greatest common factor in order to see that we do have a difference of squares. All right, next one, x squared plus 9. Unfortunately, although we have a perfect square to begin and end, I do not have a difference, which means that this is actually not able to be factored, especially with our pattern. But this one in particular is not able to be factored. The next one, we do see a perfect square with a difference in between, so we can say this is 10x. Okay, square root of the first, square root of the second, so 5 with a plus and a minus in between. It does not matter where those plus and minus go, we just need one of each. All right, so just a few examples here. You can try out that first binomial. Remember, switch it around so that you can see that perfect square and perfect square. But let's look at this word problem. Jimmy is designing a square border around a square pond. The area of the pond is 225 square feet. Use the difference of the two squares to write an expression that represents the area of the border. So really, we are trying to find, we have the area of the whole thing, which is this 2f times 2f, or 4f squared. We need to take out this pond, which is 225. Now we can factor this because it's a perfect square. It's easily factored to say 2f plus 15 times 2f minus 15. It's a perfect square, and that is the area of the border. All right, one last example here. You can try the two up above, see if they are with a certain pattern. And if a square has an area of 121 square inches, smaller square has a side length that is y inches. What is the polynomial representing the difference in the areas of the squares in factored form? So to find the difference, I would say let's do y squared minus 121. Okay, that's the difference between the areas of each of those. And we have the difference of squares to say we have y minus 11 and y plus 11. Okay, that is the difference in the areas in factored form, and this is in inches squared. You could have actually flipped them around. It wouldn't have made much of a difference. It just depends on how they are asking the question. All right. Well, I hope this is helpful for your homework and for studying.